For the buffer lab we're going to be doing next class, this problem, number 30 on page 14 of your in-class problems, will help guide you through it. Okay? Now, I made one change to letter A. Why don't you go ahead and find it and correct it? So as you can see, I changed the pH to be 6.5 as opposed to the original one I think was 7.2. Okay? So, we have the equations and equilibrium constants, Ka constants, for 3 different acids, and they're given below. All right. So from those systems above, we're going to identify the conjugate pair, so the weak acid and conjugate base, that is best for preparing a buffer with a pH of 6.5, and we're going to explain that choice. Now, honestly, technically, we could use any 3 of these conjugate pairs to make a buffer of a pH 6.5. Because let's back up a little bit. For buffers, what formula do we use to calculate pH? I know you're thinking back to last year. I mean, you learned this last year. Come on. Somebody start saying it. The Henderson-Hasselbalch equation. What is the Henderson-Hasselbalch equation? Where A minus is the conjugate base and HA is the weak acid. All right. So technically, we could use any of these acid-base systems that are given to actually make a pH of 6.5. Because what you have control over is what? What do you think you have control over in that formula? Can you control the pKa? Can you change it? No, the only way you can change it is by using a different substance, because the pKa is dependent on what? The Ka, which the Ka is dependent on the substance that it is. It's kind of like it's based on the identity of the substance. Okay, I can't take an acid and change its Ka because it doesn't make any sense. All right, so the pKa isn't going to change. So I have no control over that. So if that's set in stone, what else can I change, or what can I change about this formula? I can change this ratio. I can manipulate this ratio so that I can make the pH equal anything. But it's best to use a substance whose pKa is close to your target pH. Okay, because you're like almost there. All you have to do is manipulate the ratio just a little bit as opposed to a lot. Okay? So if our target pH is 6.5, we want to choose a system whose pKa is closest to 6.5. So what do you think we need to do with these 3 Ka values? Find the pKa, and we do that by negative log of that Ka value. So go ahead and take a minute to calculate those 3 pKa values. So what are the pKa's? What's the pKa of this one? 6 point what? 6.3? Oh my gosh. 6.38. Okay. I was hearing 6.9, 6.8, 6.3, and I'm like, those are all very different. All right, so 6.38. What did you get for the second pKa? 7.21? And what about the third one? 1.89? Okay. So which of those systems will be the easiest to make a buffer system of a pH of 6.5? The first one. Okay, because its pKa is closest to our target pH. So our conjugate pair is going to be HCO3 minus and CO3 2 minus. And the reasoning is the pKa is closest to 6.5, which is our target. Okay, so that's going to be the first part of your lab. That's what you have to do first. Let's find the pKa's of the different options and then use that to determine which pair you're going to use to make your buffer solution. Okay. Cool. No, because this is the conjugate pair. Yeah, the HCO3 minus and the CO3 2 minus. That's our conjugate pair. Okay. So now, how would we make this buffer solution? Well, there's many different ways to make the buffer system. If you had a solution containing, HCO3 minus and solution containing CO3 2 minus, and you just need to, measure out the appropriate amount and mix them together. But let me put it in terms of the way you're going to be doing it in your lab. In your lab, you're going to have access to the weak acids in solution form. All 3 weak acids that can be used for the lab will be 0.1 molar, and they're going to be available, and you can measure them out with pipette, stuff like that. The conjugate bases will be available in solid form as a salt. Okay? So, for this, which one of these is my weak acid? The HCO3 minus or the CO3 2 minus? HCO3 minus. So this is going to be as a solution. It'll be in a, we'll have that, a solution containing that ion. All right? So you'd want to measure out the specific amount of it. So measure out the specific volume of that you need. And then our conjugate base, in this case CO3 2 minus, will be in a salt. So it'll be like maybe sodium carbonate or potassium carbonate. I think for your lab, all of the salts are sodium salts. Okay. And then measure out mass of salt with CO3 2 minus that's needed, and then you'll mix. So you're going to have to do calculations based off of this part of your ratio. Okay? So what of that formula do you know? Well, you know the target pH. That's your goal, right? Do you know the pKa for your system? Yeah, that's known. That's not going to change. Do you know either of these components? Yes. Which component do you know? Do you know the concentration of one of those? You know the concentration of your weak acid. It's 0.1 for your lab, yeah. You know that, so you can calculate that. Okay? And then, do math to find grams of it. Got it? Does that help you a little bit more? And you'll write a specific procedure based off of the numbers you calculate and the actual substances you're going to be using. Okay. So now let's talk a little bit about theoretically what happens and what happens on the molecular level. And then with the next problem we'll do calculations. Okay. So for C, what if we made this buffer system, but then we doubled the concentrations? Maybe we made it again, but all the concentrations are doubled now. How would that affect the pH? That wasn't a rhetorical question. Why? Why should it not affect it? Because that ratio is staying the same. Remember, pKa isn't going to change. And if both of these concentrations double, that ratio stays the same. So pH will not change. That's kind of like the opposite of same concept of what we were talking about. What if we doubled the volume of everything, therefore diluting them both by the same amount, the ratio isn't changing, so therefore the pH doesn't change. So the pH does not change because the ratio is the same. But does it affect the buffering capacity? capacity. Buffering capacity is the ability of that buffer to neutralize an invading strong acid or strong base. Okay? It's like how much it can neutralize. So if we double the concentrations, what effect will that have on the buffering capacity? Why? Exactly. It should increase the buffering capacity because now you have more of those components available to neutralize your strong acid or strong base that's doing the invasion. Okay? So buffering capacity, buffer capacity increases because the moles, because really it's based on the number of moles of those molecules, the moles of the weak acid and conjugate base increase. Okay. Now, going back to our lab, what concentration of weak acid do you have available to you? 0.1 molar. Do you think you should dilute that at all? Knowing that a higher concentration of solutions in your buffer lead to a higher buffering capacity, leading to the fact that it can neutralize more of your strong acid or strong base that's invading, do you think you should dilute your weak acid? No. So if you dilute your weak acid, it will decrease buffering capacity. Also, you're being graded on precision here. If you make a mistake in your dilution, by diluting it, you're just adding more error, more sources of error. Okay? So keep that at 0.1 molar. Got it? Okay. And then for letter D, what if we only had a solid salt of one of our components, either the weak acid or the conjugate base? What if we only had a solid salt of one of those components available? How could we make a buffer? Can we make a buffer? Instead of in letter B where we had both components, what if we only had one? Is it possible to make a buffer from only one component? What do you think? Why not? What if I told you that last year you did make a buffer from only one component? But you did. Everyone did. Yeah, I'm talking like back in December. Oh. Jokes. Like literally last month we did that. Yeah, like what? When have you taken maybe half of something? Maybe we didn't do it at first, but then we fixed our mistake and we took half of something, neutralized it, and mixed it back together, and we got a buffer. So what lab was that? The Ka of weak acids lab. The Ka of weak acids lab, that is what we did. That's how we could make a buffer from only one of the components. You still need a strong acid or strong base to help along the way. But if you only had available to you one of the components and then, a strong acid or strong base, you could still make a buffer. Okay? All right, I'm going to actually stop this video here, and I'm going to restart. I want this video to be by itself. So, stop.